All right, hi grade 12s. Welcome back to our review series. In this short little video, I'm going to go over the wave or the quantum mechanics model of the atom. And I'm only going to go over it very briefly because I find that most students from grade 11 remember how to do this and they find it fairly easy. It's kind of like one of those things in chemistry like balancing chemical equations. Once you've learned how to do it once, you may just need to refresh, but it's usually something that kind of sticks in your mind, okay? So let's go over it briefly, and if you have any more questions, you can meet me in a tutorial later. All right, I'm going to use the solution set also, just because of that. So main ideas, remember, basically it's like, how did they figure out where the electrons are in an atom? Well, they did a mathematical equation to figure that out. And so when you've got a region of space where the electrons are generally found, they know it's a negative region because of the negative charge that the electrons have. So what do these regions look like? Well, there's lots of modeling that's gone on, and sometimes they have an orbital that's a spherical shape, and sometimes they're like these balloon shapes, sometimes they're like dumbbell shapes, and there's lots of little videos I could show you what those electron shapes, those regions look like. So I'll let you, watch the other video on that because people have fancier animations than what I have. But just remember that, right? We're going to be looking at s orbitals, p orbitals, d orbitals, and f orbitals. Are there more regions? Yes. Are they very complex? 100% they are. And the other thing I'm going to get you to think about is that, is this the last time you're going to learn about the atom and what the regions of electrons look like? The answer to that is no, okay? We're sort of on that next stepping stone because although in grade 11 and 12 we really just talk about the regions as in s orbitals, p orbitals, there's a thing where there's regions that are combined. So not only are there s and p orbitals, there's an sp orbital, okay? That's a little more complex, but just so that you know, it's not that we're just not telling you all the truth, it's just that there's a bit more to your understanding that will come in time, okay? All right, remember each level is divided into farther sublevels, and each sublevel is divided into a region called an orbital. Can I show you on the diagram at the very bottom of the page what that looks like? Okay, so here we go. If this were your orbitals and your regions, remember, you can see you've got a 1s orbital, a 2s orbital, okay? Those are orbitals. They are in the sublevel of 1s and 2s because there is only one kind of s orbital and it's spherical, okay? Each orbital can hold 2 electrons. Once you get to the second energy level, then we start reading there are 2 different types of orbitals. At energy level number 3, there are 3 types of orbitals. At energy level number 4, there are 4 types of orbitals. It gets much more complex as atoms have more electrons. Where are those electrons found? Does that make sense, right? Remember, you're always filling up from the first and moving out. So when you get to the 2p orbital, there are 2px, 2pz, and 2py. Those are the different planes at which those orbitals look like. And this diagram's hard because it really shows it best if you can see a 3D model of that. So that's why you're going to watch the video to reflect on, remember, what does that look like again? Okay, so orbitals, sublevels, and energy levels, that right there is the terminology you want to remember with regards to the wave mechanics model. Okay, every orbital can hold a maximum of 2 electrons. There are many different kinds of orbitals, and that's what's alluded to in this diagram up above. Okay, so again, energy level, number of sublevels are corresponding to the energy level. That's the same. And then, of course, S, P, D, F, and we don't get too farther than that, right? S, P, D, F, and I always remember that. I always, at the side of my sheet, I always go S, P, D, F, 1, 3, 5, 7. And what does that remind you of? That just reminds you of how many different kinds of orbitals there are. There's 1 kind of s orbital, there are 3 p orbitals, there are 5 d orbitals, and 7 f orbitals. Each orbital has a max of 2 electrons, so just kind of keep that in the back of your mind. The trend and then you can see how many electrons are going to be found in each. Okay, so if you actually had to count them all up and you wanted to see what the formula was, do you remember learning about this? If you had a question where it said, well, at the 5th energy level, how many electrons could I possibly have? What would be the maximum number? If you use the formula 2n squared, where n is the energy level, you're going to end up with your answer very easily, as opposed to having to add up all your electrons. Add that formula down. It's a handy one to remember. Okay. Do you remember the rule for adding electrons? Okay. They are all added equally, ones that have parallel spins, and then you go through and you add electrons with opposite spins. There are two ways that chemists like to reflect this or show this. Sometimes they'll show it with an orbital in a circle, and that's how we like to do it, don't we? An orbital represented by a circle in your diagram, one electron with one spin going one way, and another electron with another spin going the other way. So that diagram right there, that's an orbital with 2 electrons in it with opposite spins. You might also see it represented like this, as a line with an arrow up, or a half arrow up, and a half arrow down. Yeah, tomato, tomato, it's just how those people decided to draw that, okay? It shows the exact same thing, so you can be familiar with both of those. The next thing I want to just highlight on here is you never have to memorize the order of filling for the electrons. There are some fancy ways to do it, and I think I was taught it actually an old-fashioned way that's quite a bit harder than the way that you were probably taught to use your periodic table and to just simply count the electrons. But remember, no matter how you do it and how you represent it, the number 1 at the first, that shows you the principal energy level. The S represents the type of orbital. And you know that the little subscript there tells you how many electrons. How many electrons you've got. So 1s2 means that in the first energy level, in the s orbital, there are a maximum of 2 electrons. The next one to get filled is a 2s orbital. It also can hold a max of 2 electrons. All right, shall I do an example with you to see if you remember how to do these? We know we've got our blocks on the periodic table, so you can highlight those in a color for yourself. All you need to do, and if you don't even have to ever remember how many electrons there are in each orbital, because if you simply count the boxes on your periodic table, it tells you how many there are. Remember, an s orbital can hold 1, 2 electrons. How about a p orbital? 1, 2, 3, 4, 5, 6. A p orbital holds a maximum of 6 electrons because there are 3 kinds of p orbitals, one on the x-plane, one at the z-plane, and one in the y-plane. D, how many does it hold a maximum of? There are 5 d orbitals. Each orbital can hold 2 electrons, maximum number of 10, and guess what? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 boxes on the periodic table, so that attributes to your 10 electrons. Do I even need to go down to the F? There are 7, maximum 14 electrons. Count them if you need to. Okay, now, you remember how you go through where the D block lags behind by 1? So if you get to an element that has 21 electrons, that 21st electron isn't in a 4d orbital, it goes to a 3d. Okay, why? It's the most stable configuration. It just happens to be lower. It's how the electrons work. And when you get to atoms that have many, many electrons, it obviously becomes more complex. Okay, so if you were to have to show the electron configuration for something like, oh my gosh, what if I said cesium? 58 electrons. You got to start at the beginning. 1s2, 2s2, 3. Well, then I'd be at 2p6, right? And then I'd keep going. I'd keep going all the way, all the way, all the way here. So let's say I'm on that last little one where I filled up my 6s2. What gets filled next? Well, it comes down to here, and you should be at 6. It lags behind 2, so it starts filling up at 4f, and then I would count 1, and 2. Okay? If you need more help with that, come to the tutorial in the afternoon and I'll go over a few examples with you. But again, I usually find students have a good understanding. The only thing that's tricky is to be able to put the right answer to the question that's been given. So for example, if the question says, I need you to do an orbital box diagram, then it needs to look like this. Okay? This is correct. Let me just zoom in at the end. This is correct. It's shown all 5 for a D. This is incorrect because we know that we have to fill up the 3 electrons first. And then this is incorrect as well because we know that the 5s goes first. All right? So again, you may be asked to do an orbital box diagram. What if you're asked to do an abbreviated orbital box diagram? Maybe you'll be asked to do the full electron configuration. There's an abbreviated one. What if you're asked to, what are my other options? Oh, I guess that's all. We've gone through them all. Okay, so just make sure you understand how to do that and just do an example for each of them. And again, once you remember how to do it, move on to the next one and know that you'll be learning a little bit more the next time you take a chemistry course about this electron configuration. But don't worry, the information will just build from what you already know, and then you learn a little bit more about orbitals that are sort of grouped together, and that's called hybridized orbitals. Okay, good luck. Let me know how it goes.